Hi everyone, welcome back to chemistry. In this video, I want to talk about chemical equilibrium and something called Le Chatelier's principle. But before we talk about those things, I want to talk about something that I sort of lied to you about. So far we've been talking about chemical reactions, and we've only seen chemical reactions that are non-reversible. So what does that mean? That means we take some reactants on the left of our reaction, and we react them together and we produce our products. And I said, okay, well, anything before the arrow that I draw in the middle, that goes from left to right, anything before that arrow is, kind of our before our reaction, and anything after the arrow is what we get out after the reaction. And so far, I've only drawn this type of arrow, where and what that arrow means is that this reaction is non-reversible. So for something like a combustion reaction, right, we put in some kind of hydrocarbon and oxygen, and we get out CO2 and water. Now, there's no way to take that CO2 and water and back react it to get back the stuff you started with, right? If I burn a piece of paper, I can't get that paper back, right? It's a non-reversible reaction. Or you could think of something like baking a cake, right? I put in eggs, some milk, flour, sugar, whatever, etc., and I get out a cake. Is there any way to take this cake and back react it to make this stuff again? No, right? It's a non-reversible reaction. That doesn't happen. But there are some reactions that are reversible. So for example, one of those reactions is reacting hydrogen gas with iodine, and we get out hydroiodic acid. But what can actually happen is we can get a reverse reaction to occur where our hydroiodic acid actually back reacts and produces H2 and I2 again. So this would be an example of a reversible reaction. And when reactions are reversible, we no longer write an arrow just pointing towards the right. Instead, we now get an arrow called an equilibrium arrow. And what that arrow tells us is that this is a reversible reaction. Now, if it looks a little funky to you and you're not sure how to write the brush strokes for this, watch here. So I go half arrow to the right and half arrow to the left. I'll do that again. So why do we call them equilibrium arrows? Well, in order to understand that, we need to talk about chemical equilibrium. So chemical equilibrium is a state of a system where the rate of our forward reaction is equal to the rate of our reverse reaction. So oftentimes there are two kind of big things that we want to know about as chemists. We want to know how much product we can get from a reaction, or what's our percent yield, and we want to know the rate of our reaction, or how fast does the reaction occur. And chemical equilibrium is when we've got the same rate for our forward reaction as our reverse reaction. So just as these two are combining together and producing HI, we also at the same rate are taking our HI and decomposing it to H2 and I2. So we can look at this graph here, and we can see that on the x-axis is time, so as time goes on, and on the y-axis we have our reaction rate. How fast is our reaction occurring? And as we are reacting from our forward reaction, you'll notice that we start off with a really high reaction rate. And as we go down this curve here, we're over time, right? As we go right on the x-axis, our reaction rate is slowing. And the reason for that is if I'm reacting some H2 and some I2 and producing my HI, as I'm producing more and more HI, I've got less and less of my reactants to react with each other, right? I'm using them up. So I'm using them up, combining them, and I'm making my HI. So the rate of the forward reaction is going to slow. At the same time, when we first start the reaction over here, right, at time 0, the rate of my reverse reaction is going to be slow. It starts off really slow because at time 0, I haven't reacted these two things together and made any of this yet. Once I start making some HI, now once I've made this HI, I can start, it can start back reacting and forming back my reactants. So it's going to start slow and increase as time goes on. And at some point, the rate of the forward reaction and the backward reaction are going to meet right in the middle. And that's when we get chemical equilibrium. So chemical equilibrium can be achieved whether the reaction begins with all reactants and no products, right? Say we've only got these two things right at the beginning of the reaction. We have no HI yet. Or all products and no reactants. So for instance, we start with all of my HI and I haven't made any HI and I2 yet. Or some of both, right? We can start with a little bit of HI and a little bit of H2 and I2. And we can still achieve that chemical equilibrium. All that chemical equilibrium means is that the rate of the forward reaction and the rate of the reverse reaction are equal. All right, well, this is all fine and good, but chemists really wanted some kind of quantifiable number that could tell them, well, hey, how much of my product do I have at equilibrium? Or how much of my reactant do I have at equilibrium? Because remember, equilibrium doesn't say that the amount of our products and reactants is equal, right? It's not saying that we have the same amount of each of these. Okay, we could, but we don't necessarily. It's saying the rate of the forward reaction is equal to the rate of the reverse reaction. Those reactions are going at the same rate or the same speed. It's not saying that we have the same amount of our product as our reactant. So the equilibrium constant allows us to see, okay, well, at equilibrium, when the rate of forward and reverse reactions are the same, what is the ratio of my products to my reactants? How many products do I have at equilibrium versus how many reactants do I have? And a way that we can express that and quantify that is using something called the equilibrium constant. And we give that equilibrium constant the symbol K, capital K, and then subscript EQ for equilibrium. So, and this equilibrium constant is the ratio of the concentrations of the products to the concentrations of the reactants at equilibrium. And then what we do is we raise each of those concentrations to the power of the coefficient in the balanced chemical equation. So I know this all sounds really crazy, but just stick with me for a moment. So what do I mean by coefficients? Remember, the coefficients are just the numbers in front of your chemical species, right? So when we have some kind of balanced chemical equation, we have some kind of number in front where it's like 1 NaCl reacts with 2 Cl2s to give, whatever. So these lowercase ones are our coefficients. Those lowercase letters are just representing some generic amount of our substances, and the uppercase letters are denoting like the types of substances we have. So that's what I mean by the coefficients. So and then these brackets here, mean concentration of. Concentration of, right? So the concentration of whatever's in the brackets. The concentration of whatever's in the brackets. So for something like, let's look at C here. For something like C, the lowercase c is our coefficient. So that's going to be some kind of number, 1, 2, 3, 4, whatever ratio these react in, right, in your balanced equation. And that's what goes here. So if the coefficient right there for C is 1, then you would raise that concentration of C, your product to 1. If you had a 2 there, and let's actually make that a 2. If you had a 2 there, then this would be 2. Right? If you have a 3, you would have raised to the power of 3, raised to the power of 4, whatever. You'll notice that your products, and we'll highlight those in blue, those always go on the top of your equilibrium constant expression. And your reactants always go on the bottom. So I find that this is a lot easier, as always, to understand when we actually do an example. So let's try this, and I want to bring our equation down here. KEQ equals concentration of C raised to the coefficient C, concentration of D raised to the coefficient of D, A raised to A, B raised to B. Okay, so this is kind of our generic equilibrium constant expression. That's what this whole thing is called, our equilibrium constant expression for the previous generic reaction. So for generic reaction. But we want to write a specific equilibrium constant expression for our own reaction that we're looking at. So for example, it says write the equilibrium constant expression, KEQ, for the following reaction. And then we have this balanced equilibrium equation where we have nitrogen gas plus hydrogen gas in equilibrium with ammonia gas. Okay, so we want to write our equilibrium constant expression. So I know I'm going to have KEQ on the left of my equation. And then on the right, we need to know the ratio of our concentration for our reactants versus the concentration of our products. So let's try this out. So remember that the products go on the top, raised to their stoichiometric coefficients, and the reactants go on the bottom. Reactants go on the bottom. So these are the reactants. And you don't have to put these states in there, so you don't need to tell us that it's a gas in your equilibrium constant expression. But we do need to write some other stuff down. Okay, and then in the blue is our products. So we need our brackets, because that tells us that it's the concentration of our product at equilibrium. So for NH3, that is our product. Now we want to know, we need to raise it to some coefficient, right? So what is the coefficient in front of NH3, our product? Yeah, 2. Okay, and I know there's another spot here where we could put some other reactant, or some other product, sorry, but we don't have another product, so we just leave it like that. All right, so on the bottom, now we've got our brackets for our first reactant. What's our first reactant? Yeah, N2, and it's raised to what power? Yeah, just 1. There's no coefficient here, or there's just an imaginary 1, so we just raise it to the power of 1. And then we have another concentration bracket, right, for our second reactant, which in this case is H2. And we need to raise that to the power of what? Yeah, 3, because that's our coefficient here. Okay, and that would actually just be your answer. So notice that you're not actually solving anything here. We're not getting some kind of number out of this yet. We will in the future, but if a problem just says write the equilibrium constant expression for the reaction, that's what we've done here. We've written the equilibrium constant expression. We haven't solved anything because we don't even know what concentrations we have of these different reactants and products. But if we did, we could plug in those numbers here, here, and here, right? And get some kind of number out of that. Okay, so let's try this again. So remember, it's KEQ. And now I'm going to show you kind of another generic way of writing this. So you can also think of it as the concentration of your products raised to the power of X over the concentration of your reactants raised to the power of Y. Okay, so let's see. We have we know we're going to have KEQ on the left equals. And now we've got our reaction here. So remember, our products go on the top and our reactants go on the bottom. So reactants I'll leave in yellow, products I'll put in blue. And our products are CO raised to the power of what? Yeah, 2, because we've got a 2 here in front of our CO. That's our coefficient there. And then multiplied by O2, the concentration of O2. Remember those brackets. Raised to the power of what? Yeah, just 1. All of that divided by the concentration of our reactant. This time we only have 1, so we'll just have 1 thing in brackets down there. Raised to the power of what? Yeah, 2. And that is our answer. This is the equilibrium constant expression for that reaction. All right, so why do we actually care about KEQ, or our equilibrium constant? What does it matter? So this equilibrium constant expression can actually tell us if the reaction favors products or reactants at equilibrium. So if your equilibrium constant is some value, we can use that value to tell us, oh, our reaction favors products at equilibrium, which means I have more products than reactants at equilibrium. Or maybe my KEQ shows that my reaction favors my reactants at equilibrium. So I have more reactants at equilibrium than I have products. So here's just kind of like a quick cheat sheet for what a K value means. So for instance, right, what we're going to do eventually is we're going to plug in some concentrations for these numbers here. And eventually we're going to get some number out for KEQ. And that number can either be small or large. When K is a very large number, the reaction is essentially irreversible. So what does that mean? It means you're mostly going to have products, right? A large K, or KEQ, means you have mostly products. And what do I mean by large? Well, I mean a K value that's greater than 1,000 or 10 to the third. So some really, really large number. If K is a very small number, the reaction produces almost no products. So we only have reactants that are present at equilibrium. So that's on this other end. And that's when K is less than 10 to the negative third. Right? We've got mostly reactants at equilibrium. So we have a small K value, and we produce almost no products. Large K value, we produce almost all products, or all products. And then anything in between is kind of intermediate, where you've got, a K value that is in between 10 to the negative third, or 1,000th, and 1,000. So if you've got, a K value that's between 1 and 1,000, you've got maybe more products than reactants at equilibrium, but still kind of intermediate. When K is between 1 and 0.001, you've got more reactants than products at equilibrium. Okay, so let's try this out. Now we're actually going to get a value out of our KEQ. So this says, a chemist runs the reaction shown below and measures the following concentrations at equilibrium. So notice, right, remember, anytime you see brackets, that means concentration. Okay, so we've got some kind of concentration. What's this M, this big M here? Yeah, that stands for molarity, right? Molarity is a way of expressing concentration. It's a unit of concentration. So we know our concentration for N2O4, for our reactant, and we know our concentration for NO2, our product. So if we know those concentrations, we can actually write an equilibrium constant expression and then plug in these values into our expression. So first off, we need to figure out our equilibrium constant expression. So write KEQ expression. That's our first step. So we know KEQ is going to be on the left. And then remember, it's KEQ equals products. Whoops. That looks weird. Products raised to some coefficient. And then reactants on the bottom raised to some other coefficient. Okay, so our KEQ for this one, we need the products on the top, right? So what's our product here? Yeah, NO2. And it's raised to what power? 2, yep, because we have a 2 in front. That's our coefficient. And then our reactant goes on the bottom. That's N2O4. And what power is that one raised to? Yeah, 1. You can either write the 1 there or you can just leave it blank. I'm just going to leave it because we don't, anything to the first power is just that thing itself. So let's go ahead, and now we have our equilibrium constant expression. And so we can start plugging in, these values in there. So let's say 2, plug in values. So we have KEQ equals, now what is the concentration of NO2? Yeah, the thing in blue, right? 0.0172, and I'm going to leave my unit in there, molar. And then what's our concentration for N2O4? Yeah, 0.00140 molar, right? Just taking those concentrations up here and plugging them into the correct spots on our equilibrium constant expression. Okay, so we got to get a number out of that. And I got 0.2. Let's go 0.211 for 3 sig figs. So that's our KEQ. We got a value out of that because we knew our concentrations and we could plug them in. So our KEQ is 0.211. So let's take a look up here and let's think about, is that a small number or a large number? Well, our KEQ is 0.2, so it's it's less than 1. So it's definitely on the smaller end. It's definitely not large. But it's not quite less than 10 to the negative third. 10 to the negative third is 0.001. So it's not quite less than that. But, so it's not all reactants, so it's somewhere in the middle, but it's actually between 1 and 0.001, so we're definitely going to have more reactants than products at equilibrium. So this one, we would say the reactants were favored. All right, let's try this again. So we have our KEQ equals products, concentration of our products raised to some power, over the concentration of our reactants raised to some power. Okay, so KEQ here, let's go ahead and get a equilibrium constant expression out of this. Actually, we should read our question first. So it says the reaction between gaseous sulfur dioxide, SO2, and oxygen, O2, is a key step in the industrial synthesis or making of sulfuric acid. A mixture of SO2 and O2 was maintained at 800 Kelvin until the system reached equilibrium. And at equilibrium, the mixture contained these concentrations for our reactants and products. And then it says to calculate the KEQ. So we know KEQ equals the concentration of our products. Again, let's do some color coding here. So our product is SO3 raised to the power of 2 because we've got our coefficient there is 2. And then our reactants, we've got SO2 raised to the power of 2 because that's our coefficient. And then O2 raised to the power of 2. Oops, nope, raised to the power of 1, sorry. All right, so now we've got a equilibrium constant expression that we can plug numbers into. So we'll call that step 2. So KEQ equals, sorry, that's a Q, equals, let's see, so this is our product, SO3, and these two are our reactants. So we've got 5.0 times 10 to the negative 2. And I apologize. I think I said earlier to put the unit here for, whatever unit you have. You actually don't need to do that because our equilibrium constant is going to be unitless. So there's no units there. So you don't need to put it in there. Okay. And then on the bottom, we've got SO2. That's going to be 3.0 times 10 to the minus 3, right? Just taking this concentration here. And remember, that's raised to the power of 2. And then we've got multiplied by 3.5 times 10 to the minus 3. And that one's just raised to the power of 1. All right, so let's get rid of some of this, clean this up a little bit. And now we've got to get a number out of all that. And I got that our KEQ equals 79,365. And that was our KEQ. Now that's a really, really large number. So right away I'm looking at that and I'm thinking, I'm gonna bet that that favors mostly products at equilibrium, but let's just double check on our chart up here. Get rid of all this. Yeah, so 79,000 is a lot higher than 1,000. So this is definitely a large K value, which means we're only gonna get products out at equilibrium. All right, now there was a French chemist named Le Chatelier, credited with discovering that when a chemical system that's at equilibrium is disturbed by some kind of stress, the system will respond in order to relieve whatever stress was applied. And what do I mean by stress? Well, stresses to a chemical system are things like we change the concentration of our reactant or product, right? We add more reactant or we add more product or something like that. Or something like changes in temperature, right? We increase the temperature on a chemical system and that adds a stress. Or we change the pressure of a system. So all of these different kind of stressors, if we add these stresses to a chemical system that's already at equilibrium, that system is going to try to relieve that stress, right? Just like us when we are feeling unbalanced, right? We were totally doing fine and then something stressful happens and we immediately want to correct that stress and get back to equilibrium. Same idea here with Le Chatelier's principle. So one of those stressors was concentration, changing the concentration. So if the concentration of one substance in a system is increased, the system is going to respond by trying to remove that substance. So if we add reactants and we now produce more products, the system is going to want to remove that change and get back to the same number of reactants we started with. So for instance, say that we have this reaction here, our nitrogen plus hydrogen gas at equilibrium with ammonium. Now, how is this question asks, how will it affect the reaction if equilibrium is stressed by each change? So say we add more H2, right? We increase the concentration of H2. We add more of this thing. Now, what's going to happen if we add more of this? There's going to be more of this to react with this, more H2 to react with N2, and we're going to end up we're making more of our products. So we would say that the reaction will shift to the right. That's how we say that. The reaction will shift towards the right, or towards the products, whichever way you want to put it. Okay, we've added more H2, our reaction was at equilibrium, now it's super unbalanced, and it's going to try to correct that change by producing more of this thing in response, or more of our product in response. Okay, let's try this. NH3 is added. So now, instead of increasing the concentration of H2, we are now increasing the concentration of NH3. Well, what's going to happen? Well, now we've got more of this. If in our container, we've got more NH3s to react, right? Then what's going to happen is they're going to react together and we're going to produce more of our reactants. It's going to back react more. There's more of that thing to react, so we can make our reactants. And so the reaction, we would say, will shift towards the left, or the reactants. All right, now say we remove NH3. We decrease the concentration of NH3. Now there's less NH3 in our vessel to react, and we can't make as much of these two things. So now the reaction is going to shift this way. right? We no longer can back react because there's not enough of this to back react, right? So we can't get back our reactants. So if you decrease the concentration of something, the system is going to respond in such a way that you counteract that change, okay? And we're going to try to produce more of our products. All right, so reaction will shift towards the right. So here's a little bit of a summary slide that might help with this. So if we add our reactant, if we add one of our reactants, we're going to favor the forward reaction, or in other words, we're going to shift right. Now, if we add some more of our products, right, then our reverse reaction is going to be favored, or we're going to shift left. If we remove our reactant, it's the opposite, and we're going to favor the reactants, shift left. And if we remove a product, we're going to shift right, because our forward reaction is going to be favored. All right, another factor that, or stressor that can affect our system, according to Le Chatelier, is temperature. So if we increase or decrease the temperature of a system that's at equilibrium, that also adds stress to the system. All right, so looking at this example here, we've got N2 reacting with H2 to give NH3. And it turns out that this reaction is exothermic. Now, I know that because, remember, exo means releases heat, right? Releases heat. So exiting, I think of releasing as exiting, exothermic. So if we release heat, if we have an exothermic reaction, at the end of the reaction, we're going to get our heat energy out. So we write it as a product because we're releasing heat. An endothermic reaction would have heat on this side if it was endothermic. It's not, so it has heat on this side. Sometimes you'll actually see, instead of 91 kilojoules, some kind of unit of heat, you'll literally see the word heat. Okay, so plus heat. And that's another, you could think of it as another product. Heat is another thing that's produced. Just like when we talk about combustion reactions, sometimes I said you'll see something like this. And it means the same thing. It's just showing us that, hey, this reaction produces lots of heat. Okay, so if we think of heat as a product, if we increase the temperature, it's like we're increasing another product, right? Just like when we increased the amount of our product up here. If we added some of our product, what happened to the equilibrium? Well, it doesn't like that we now have more stuff on this side, so it's going to shift to the left to counteract that change. It's the same idea with temperature. If you think of it as a product, if you're adding in more heat, that's going to make our equilibrium want to shift in the opposite direction because we've now added a product. So let's try this out. So this says, predict the effect of increasing the temperature on this equilibrium. So we've got phosphorus trichloride plus chlorine gives phosphorus pentachloride and lots of heat. Okay. All right. So this is an exothermic reaction. Exothermic means heat is one of our products. We could think of it like that. So if we increase the temperature of this reaction at equilibrium, we're going to increase the amount of this heat we have, which increases a product. And which way is the equilibrium going to shift? Yeah, it's going to want to counteract that change. So equilibrium is going to shift to the left, and we're going to make more of our reactants. Wants to counteract that change. Now, what if we have an endothermic reaction where heat is on the left side of the equation? It's a reactant. Heat is a reactant. Now this says, predict the effect of decreasing the temperature on this equilibrium. So we're going to decrease thinking of this as a reactant, we're going to decrease the amount of that reactant. So just like when we talked about concentration, if we decrease the amount of that reactant, we no longer have these two things reacting together and we can't produce this thing anymore. So, or you could think of it as our reaction is going to shift to the left. Our reaction doesn't like that we decreased stuff on the left side. So it wants to increase the stuff on the left side again to get back to equilibrium. And that means it's going to shift to the left. So shifts left. And I think I forgot to write, shifts left up here. Okay. All right, now for pressure, this is our last stressor that Le Chatelier talks about. So we can change the pressure of a system, and that's going to put a stress on a system as well. So say we have, again, our chemical reaction at equilibrium here, and say we originally, at time A, we have our pressure with this kind of movable piston here. We've got our pressure at, this is going to be a lower pressure system because we've got quite a bit of volume there for those gas particles to move around in, and we don't have too much pressure. But say we increase the pressure, right? Increase pressure. Le Chatelier was interested in understanding, well, if we increase that pressure, how does that affect equilibrium? And what we found was that a pressure increase, right, like we've done here, is going to shift the equilibrium to the side of the reaction with the fewer number of moles of gas. The side of the reaction with the fewer moles of gas. So in this case, we've got 1 mole of N2 and 3 moles of H2. So for gases here, we've got 4 total moles of gas on the left. Whereas on the right, we've got 2 moles of gas. So if we increase the pressure, what Le Chatelier found was that the equilibrium is going to shift to the side of the reaction with the fewer moles of gas. So in this case, increasing the pressure is going to cause the equilibrium to shift to the right. So you have to count the moles of gas using your balanced chemical equation. Now, say we decrease the pressure. Say we decreased the pressure. How is that going to affect equilibrium? Well, if we decrease the pressure, that's going to shift the equilibrium to the side of the reaction with the greater moles of gas. So actually, let's put this in green. And then we'll go this way. If we decrease the pressure, we're going to shift our equilibrium to the side with the greater number of moles of gas. All right, so let's try this out. This says, what is the effect on this equilibrium if pressure is decreased? So if we decrease the pressure, our reaction is going to move in the direction that counteracts that change. So we first need to look at how many moles of gas we have on each side. So on the left side, we have 3 moles of gas. And on the right side, we have 2 moles of gas. So if we decrease the pressure, our reaction is going to shift to the left because we want to increase the number of moles of gas that are pushing on the walls of the container to reestablish equilibrium, to get that pressure back up to where it was before. The more particles you have moving around in that container, hitting the walls of the container, causing collisions, the more collisions you have, the higher the pressure. So that's going to increase the pressure again. So the equilibrium is going to want to shift left in this particular problem. What if we increase the pressure? Which way would the equilibrium shift? Yeah, towards the right. We want to get less of those moles of gas pushing on the outer walls of the container, so we're going to favor the side with less moles of gas. All right, here's a summary. Say, we increase the pressure, right? What is the response? Well, the reaction is going to produce fewer gas molecules. And then if we decrease the pressure, the reaction is going to produce more gas molecules or more moles of gas.